Hi there, and welcome to this lesson on Further Pure Mathematics 2. And in this lesson, we're on Chapter 8, 8.3, and looking at the area enclosed by a polar curve. Now, it's the area which is enclosed by the curve and two half lines. And the angle made by those two half lines are the limits that we use in the integral. And the half lines come from the pole. So the area, where theta is measured in radians, is given by the formula. The area is equal to the integral between alpha and beta of a half r squared d theta, where a half r squared obviously has close relations to circular measure. Before we do the first example, you'll notice that there are three formulae written above it. One is the formula for the area of a curve, written in polar form. Now, that formula is in the formula book for the International A-level. These other two formulae are used a great deal in A-level maths when you're having to do integration with trig functions. Neither of these formulas is in the formula book. The only formula that is there is the formula for cos A plus B. And you can derive these formula from that. But it does mean that you either need to learn these formula or you need to be confident that you can derive them from the formula for cos A plus B. Okay, example 1. Find the total area enclosed by the cardioid, r equals 6 into 1 plus cos theta. And the first thing to note is that unlike with Cartesian coordinates, we don't have to worry about areas beneath the x-axis giving negative areas. Now, because the curve is symmetrical, if you wanted to, you could find the integral from 0 through to pi and then double that to get the whole area. What I will do is I'll just do it in one go, and I'll do the total integral from 0 to 2 pi. Okay, I'll let you have a go at finishing that question off yourself. So pause the video, have a go at completing it, and then come back to me when you're ready. Okay, let's have a look at that. So this first line, we've just written down a half r squared. R squared is 6 squared, which is 36, and then 1 plus cos theta squared. Multiplying out the brackets and doing the half times the 36 and taking that out of the integral will give us that. And it's at this point where we need to change the cos squared theta using the trig identity into a half into 1 plus cos 2 theta. Just because it's a great deal easier to integrate, that's all. Tidying that up a bit gives us that. And then integrating that, the integral of 3 over 2 is 3 over 2 theta. The integral of 2 cos theta is 2 sine theta. And the integral of a half cos 2 theta is a quarter sine 2 theta. Then we just need to put in the limits, 0 and 2 pi. Putting in 2 pi, we'll get 3 times that divided by 2, which is 3 pi. The sine of 2 pi is 0, and putting theta equals 0 into all of these three things also gives us 0. So this very, very quickly simplifies to a total area of 54 pi. Example 2, find the total area of the 3 loops in the rose curve with equation r equals 2 sine 3 theta. Now, there is an issue with integrating here, which is that the curve is only defined for certain regions. So from 0 to pi by 3 it's defined, but then for this region between pi by 3 and 2 pi by 3 radians, the curve isn't defined. What that means is if we're going to find the area of the 3 loops, we do need to find the area of just one of the loops and then multiply that by 3 to get the answer. Okay, I'll let you have a go at doing that. So pause the video, have a go at finishing the question, and then come back to me when you're ready. Okay, let's have a look. So as we said, between 0 and 2 pi, when r is negative, the graph is not defined. Therefore, we need to find the area of one loop using the correct limits and then multiply by 3. So the area of one loop, and I'm looking at this first loop here on the top right. That begins at theta equals 0, and then as we go around the curve, we get to theta equals pi by 3 when we return to the origin. So that top loop will be the integral between 0 and pi by 3 radians of a half into 2 sine 3 theta squared, just substituting into the formula there. Squaring the brackets and dividing by the 2 outside will give us the integral of 2 sine squared 3 theta. And then we'll need to use the identity that we had on the first question, which is that sine squared theta is equal to 1/2 into 1 minus cos 2 theta, which means that sine squared 3 theta is 1/2 into 1 minus cos 6 theta. Multiplying out the brackets, it simplifies to that, and then integrating that gives us theta minus 1/6 sine 6 theta. Now we just need to put in the limits, pi by 3 and 0, and that'll give us pi by 3, and again when we substitute in 0, we just get 2 zeros, and the sine of 6 times pi by 3 is also 0. So the area of one loop is pi by 3, which means that the 3 loops all added together will give us a total area of exactly pi. Okay, that gets us to the end of this lesson. If you've got the textbook, then turn to page 160 and have a go at exercise 8C. Thanks very much for listening, and cheerio.